Welcome everyone to a new edition of the virtual seminar on geometry with symmetries. Today I have the pleasure to introduce my collaborator Elia Fusi from the University of Turin, Torino, in Italy. And Elia will be talking about homogeneous generalized Ricci flow. Thanks, Elia.
Okay, so thanks Ramiro for the presentation, and before starting with the talk, I just want to thank the organizer for the invitation to this seminar. And so in this talk, I want to present a joint work with Ramiro from UQ in Brisbane, and with James Stanfield from Münster, concerning the homogeneous generalized Ricci flow. So the main outline of the talk will be the following. So in the very first part, I want to discuss a bit what motivated us to study this such flow, and in particular motivation coming from complex geometry. And so I want to discuss a bit the connection between the generalized Ricci flow and the pluriclosed flow, which is another geometric flow arising in some sense naturally in the context of complex geometry. Then I'll move to the homogeneous setting, and I want to discuss a bit about homogeneous generalized geometry and what we call the moving Dorfman bracket approach. And then in the last part of the talk, I want to present some results concerning the behavior of the generalized bracket flow on both solvable and nilpotent Lie groups. So let me start. Just before starting, the talk might be quite technical, so please stop me whenever you want to ask questions or comments and whatever. So let me just start with introducing you the flow which we will analyze. So our starting point is just a Riemannian manifold with a closed triform H naught. And then the generalized Ricci flow is this following coupled system of equation, one for the Riemannian metric, which evolves in the direction of these two symmetric two tensor, Rich B, and the other for the closed triform, which will evolve accordingly to a classical 8 equation. Where here this symmetric tensor Rich B is constructed out of the classical Ricci tensor and this symmetric tensor H squared, which is again constructed starting from the triform. So on any vector field x and y, we're just computing iota x of h and iota y of h, and then pair them together. So what we constructed is a symmetric two tensor, and we join this tensor with the Ricci, the classical Ricci one, to obtain this Ricci B. So I should remark here that I'm quite abusing the notation, because the generalized Ricci flow born as a flow of Riemannian metric and two forms, evolving in the direction of minus this star of H, where H is evolving within the cohomology class of the starting triform we choose. But of course, the evolution equation of the moving triform will be the one that I reported, so I will refer to the generalized Ricci flow as this flow of Riemannian metrics and triforms. So our first motivation to study the generalized Ricci flow is the fact that it comes and was born in theoretical physics, in particular in string theory, and its first name was the renormalization group flow. But more from a mathematical point of view, the motivation, at least for us, to study the generalized Ricci flow comes from the realm of complex geometry. We know that on an Hermitian manifold or a complex manifold, we can pick various concepts of special metrics. And for us, the most relevant will be the SKT one. So let me just fix an Hermitian manifold, and the Hermitian metric G will be called SKT, or pluriclosed, if the fundamental form omega associated to the Hermitian metric is the DC closed. Here, this is the real operator constructed out of the classical exterior differential and twisted with a complex structure J. And these metrics, in some sense, have this type of metrics has attached to them a special canonical Hermitian connection, which is called the bismuth connection, and was firstly introduced by Strominger in the physical setting, and then by Bismuth in a more mathematical setting, which is nothing but the unique connection which makes both G and J parallel and has skew-symmetric torsion, totally skew-symmetric torsion. So what we obtain is a tree form, and one can actually easily show that this form is up to assign the DC of omega. And so in some sense, SKT metrics are the one satisfying an additional property on the torsion of the bismuth connection. Indeed, as you may see, an Hermitian metric is SKT if and only if the torsion of the bismuth connection is declosed. Okay, we have plenty of examples of SKT metrics, but for the purpose of this talk, I want to present, to give you some of them. And the first ones are, in some sense, found by result by Goduchon, which specialized in the case of complex dimension 2, says the following. On any compact complex surfaces, we can actually find an SKT metric in any conformal class of a given Hermitian metric. This will be quite important while discussing some conjecture about the pluriclosed flow that I will introduce in a few minutes. And then other example can be found in the locally homogeneous setting on compact quotient of Lie groups. And then I listed some of works by, for instance, Fino, Farton, and Salomon on three-dimensional Lie manifolds, and by Fino and Paradiso on almost abelian solved manifolds, and almost nilpotent ones. But as I was saying in the introduction, we thanks to work by Strizentiano, we got the realm of SKT metrics, a natural geometric flow, which is the so-called pluriclosed flow, which evolves an initial Hermitian metric in the direction of this tensor, minus S plus Q, where S is the so-called second chair Ricci tensor, while Q is an appropriate quadratic expression in the torsion of the chain connection. But most importantly, this definition can be given on any Hermitian, starting from any Hermitian metric. But if we specialize in the case of the starting metric being SKT, what we can observe, and this is again due to Strizentiano, is that the pluriclosed flow starting from such metric will preserve the SKT condition. And of course, it has on compact manifold short-time existence. And so if we start from an SKT metric and we run the pluriclosed flow, the solution will be SKT for any time of existence. And we can go even further and relate this pluriclosed flow to curvature tensor built from the bismuth connection. Indeed, if we look at the pluriclosed flow, can be equivalent restated as a flow of 1-1 forms, starting from the fundamental form of the initial Hermitian metric and flowing in the direction of the 1-1 part of the bismuth Ricci form, which is a two-form constructed out of the full curvature tensor of the bismuth connection. And there are many conjectures that are still open concerning the pluriclosed flow. And the first I want to show you is a conjecture, again, due to Stritz and Tian, which in some sense mimic the behavior of the Keller-Ricci flow. We know that the Keller-Ricci flow will exist for some maximal time, and where this maximal time of existence is purely characterized by cohomological aspects of the manifold we are on, and on the Keller class of the initial metric. And then on the Keller-Ricci flow, we know that this is true. The maximal time of existence of the Keller-Ricci flow is precisely this cohomological quantity. And so Stritz and Tian conjecture that actually the same holds for the pluriclosed flow. So if we start from a compact SKT manifold, we can cook up this number, which is built out of the Epley cohomology class of the starting SKT metric, and this generalization of the first chain class of the manifold. And then the conjecture states that the pluriclosed flow will exist in this maximal time interval of existence, where the extremal value is precisely the cohomological quantity we defined above. And at the end of the talk, we will see that this conjecture is actually true, at least on solvable Lie groups or quotient of them. But concerning complex surfaces, again, Stritz conjectured the following. So if we start from a compact complex surface of class 7+, then the behavior of the pluriclosed flow is in some sense conjectured to have the following behavior again. So starting from any SKT metric, which we know that there will exist from Gudauchon theorem, the pluriclosed flow will exist for any time and will converge to, in the Shiger-Gromov sense, to a non-flat complete steady soliton, which in some precise sense detects a global spherical shell. And so if this conjecture was to be true, then it will in particular give a proof of the global spherical conjecture, and so giving a full classification of compact complex surfaces. So the pluriclosed flow has many open questions to be answered, but and starting from them, most importantly for us is the connection between this flow and the generalized Ricci flow. So thanks to again results by Stritz and Tian, we know that if we start from a solution of the pluriclosed flow, then the Hermitian metric and the torsion of the bismuth connection will evolve accordingly to this coupled system of equation. But here the theta is a one form, which is called Lie form, and is defined as follows by this implicit equation. And so, as you may see, this coupled system of equation differs from the generalized Ricci flow up to a time reparameterization by 2 and up to gauge terms, where the vector field is precisely the vector field associated to the Lie vector field. And then we can actually say the following. So if we have a solution of the pluriclosed flow, then up to a time reparameterization and a gauge fixing choice, the metric and the torsion of the bismuth connection will be a solution of the generalized Ricci flow. On the other hand, in the pluriclosed flow, we know that the complex structure will stay fixed. While doing this gauge fixing choice, we need to move also the complex structure. And so the Hermitian metric and the torsion of the bismuth connection will be a solution of the generalized Ricci flow once we couple it with the following evolution equation for the complex structure. But that's really an important motivation for us to go through the study of the generalized Ricci flow, because as you may see from this theorem, one can study the behavior of the generalized Ricci flow and then obtain information on the behavior of the pluriclosed flow by some gauge fixing choice. And so this is what we decided to do, to study the generalized Ricci flow. But before going into the discussion of the generalized geometry setting, let me just state some state of the art. So first result I want to give you is the following. So if we start from any initial datum and we run the generalized Ricci flow on its maximal time of existence, if the maximal time of existence is finite, then what it has to blow up is the norm of the full Riemannian tensor, curvature tensor. And another result, which was proven by Stritz and Tian again, in some sense improve the previous one, but just on the case of the pluriclosed flow. So as before, we run the pluriclosed flow from any starting SKT metric, and we assume that it has finite maximal time of existence. Then what has to blow up as the time approaches the maximal time of existence is this quantity, which is built from just the 1-1 part of the bismuth Ricci form. And so in some sense, this result is an analog of the Cesum result for the classical Ricci flow. And as we will see at the end of the talk, at least in the homogeneous setting, we can go even better, and we to have long time existence, or if we assume to have finite time of existence, what has to blow up is a quantity, and a scalar quantity, which will be called the generalized scalar curvature. Another important result is that as the Ricci flow, the generalized Ricci flow is a gradient flow of this suitable operator, defined out of a Perelman type functional f, where here just the difference between the classical Perelman function and this is this term, which is given by the square norm of H, with this apparently strange scaling. But as we will see in a moment, this quantity, this scale minus a 12 the norm squared of h will be an important quantity for us, and it's precisely what we call what is called generalized scalar curvature. Focusing on the homogeneous setting, as a difference between the Ricci flow, we know the existence of a non-flat homogeneous fixed point of the generalized Ricci flow. This is due to Raffaele and Podestà, and then by Laurette and Will. And moreover, we got again, thanks to the work by Raffaele and Podestà, a generalization of the Bryant soliton. So we got a generalized steady soliton with SO3 symmetries in 3 dimensions. So let me just now give some preliminaries of generalized geometry, because it's the setting we use the most for our study. So I will present just the toy model, let's say, of generalized geometry, which is the generalized tangent bundle. So we fix our smooth manifold and a closed reform on that. We can build the so-called generalized tangent bundle, which is the direct sum between the tangent and the cotangent bundle. And then on section of this bundle, we can cook up the so-called neutral inner product, which is just given by the natural pairing between one form's vector fields. The so-called anchor map, which is in this case is just the projection onto the first factor, and the H-twisted Dorfman bracket, which is built out of the brackets between vector fields and the closed form H we fixed above. And these 3 objects will satisfy many properties that I want to list you. The first one is that the Dorfman bracket satisfies the Jacobi identity, which will be quite important later, in the sense that the adjoint action of cooked up with this bracket will act by derivation, while the anchor map is in some sense a Lie algebra homomorphism. But on the other hand, of course, the Dorfman bracket will not be a Lie bracket, because it won't be, in general, skew-symmetric. But we precisely know how it lacks to be skew-symmetric, and this is the quantity. And then we got plenty of other compatibility condition between these 3 objects. The first one is the following, and then we got some sense a Leibniz rule with the functions. And altogether, this we can summarize saying that the presence of a closed reform determines the so-called exact current algebroid structure on the generalized tangent bundle. And to shorten the notation, I will refer to it as just the generalized tangent bundle endowed with a 3-form H, closed 3-form H. So we got this new structure, and it will be quite important for us to analyze isomorphisms of this structure. So an isomorphism between these 2 exact current algebroids will be just a pair of consisting of a diffeomorphism between the base manifolds and a vector bundle isomorphism, which covers the little f, the diffeomorphism, which of course has to preserve all the structure we have. So let me say just that the action by base change, in some sense, will act of f on the first neutral linear product will precisely give the second one. And again, the action by base change on the first Dorfman bracket will give precisely the second one. And if we specialize in the case of automorphism, we got a full characterization of the group of automorphism of the generalized tangent bundle with a closed T-form H. And this group is constructed out of two types of maps. The first one is just the natural lifting to the generalized tangent bundle of the action of a diffeomorphism, while the second one is quite new and is not appearing in the classical Riemannian geometry and is built out of a two-form B, which can be seen as an endomorphism between the tangent bundle and the cotangent bundle, so we can exponentiate it to have the following automorphism, and then all the other will be produced by composing these two types of maps. But of course, we got to impose some compatibility condition, and so the compatibility condition is the following. So in other words, the diffeomorphism F has to preserve the homology class of H. But this group is an important part of our work, because at some point we need to act with some Lie group, and the guideline in some sense is given. The choice was guided from this automorphism group. Now we can go to the metric part. So on our manifold, we can fix a Riemannian metric and again a two-form B, and build this endomorphism. So we act by the same exponential of B on this endomorphism built just from the Riemannian metric. This endomorphism will satisfy, again, some properties, which are the following. So will be orthogonal with respect to the neutral inner product, and if we put it in the first entry of the neutral inner product, what we obtain is a symmetric and positive definite bilinear form on sections of the generalized tangent bundle. And so this type of endomorphism will I will refer to it as generalized matrix, and use this notation for the full space of generalized matrix. And then if we got an isomorphism between two exact generalized tangent bundles endowed with two generalized matrix, we can, of course, talk about isometries, which are just isomorphism which conjugates the first generalized metric to the second. Now we want to build some curvature quantities, and this was the most general setting was given by Mario Garcia Fernandez, and this endomorphism I just presented just in the special case of B equal to 0 is the so-called generalized Ricci curvature, which is again built from the tensor Ricci B and the star of H. And we can even go further and define what is called the generalized scalar curvature, which is precisely the quantity appearing in the Perelman type functional I presented before. But this is of course this is what we were concerned on the most, and we will see how this quantity will enter the game in the homogeneous case. And then now we have a Ricci curvature. We can flow the generalized matrix starting from an initial one in the direction of this generalized Ricci curvature. This is the so-called generalized, this is a flow of generalized matrix which was proven to be equivalent to the actual generalized Ricci flow that I presented before. And so what we obtain is an equivalent rewriting of the generalized Ricci flow just in terms of a flow of generalized metrics. And this is the setting we want to perform our study. So let me now just go into the homogeneous setting. So for the simplicity, again, I will focus on the Lie group case. So we fix again a closed tree form on the Lie group G we fixed, and a generalized metric. So our metric generalized tangent bundle with the generalized metric will be said left invariant if all the classical datum are left invariant. Or more generally, this is actually equivalent to saying that the action by left translation on the group can be lifted to the generalized tangent bundle, obtaining an action by isometries. And of course, I'll refer to the space of left invariant generalized metrics as this symbol GM with the upper script G. And as I was mentioning before, we want to move by the action of a certain Lie group, which resembles a bit the automorphism group that I showed you before. And the group we choose is the following, which is again built from the two maps. One is the natural lifting of an element in GLG to the generalized tangent bundle, and the other one is the same as in the isomorphism group. So we pick a left invariant to form, and we exponentiate it as before, obtaining an endomorphism of the generalized tangent bundle. And so composing these two maps, we obtain what we said called the Lie group L, which will act by orthogonal transformation on the neutral inner product. And as one can, of course, compute the Lie algebra of L, which has the following representation. Okay. So a first remark that I want to do is that due to the form of L, which has no upper right corner, the generalized Ricci curvature will not lie in general, of course, in the Lie algebra of L. But on the other hand, we can actually show the existence of a unique element, this AGH, lying in the algebra of isometries, so that the difference between this element and the generalized Ricci curvature will lie in the Lie algebra of L. And so morally, we are just modifying the generalized Ricci curvature in a way that doesn't affect too much the generalized geometry of the manifold. Indeed, and this is shown by saying that this is actually an element on the Lie algebra of isomorphism. And so we are just fixing a gauge choice where all the diffeomorphism or automorphism are isometries. And another important proposition we showed is that this Lie group L will act transitively on the space of left invariant generalized metrics by the natural action by conjugation, as I showed you before. And more importantly for us is the following. So any element in the Lie group L, this little l, will give rise to an isometry between these two exact current algebroids. Where, as you may see in this in the right exact current algebroid, we are acting with the element L on the generalized metric. And so this can be thought as the classical setting where we are varying the generalized metrics, and we study the generalized geometry as this metric varies. while the first exact current algebroid is fixing the generalized metric while is acting with the element L on the Dorfman bracket. And so in some sense, this represents the moving Dorfman bracket approach or framework, where we are fixing the generalized metric and we are actually studying how the generalized geometry changes as the Dorfman bracket change. And this setting or framework is what we study, of course, the most. But before going into the discussion, we want to study a bit better the set of Dorfman brackets. So in this case, in the left invariant case, these elements will be skew symmetric, will satisfy the Jacobi identity. Moreover, the following three-tensor is skew symmetric, and it's in particular closely related to the tree-form H. And moreover, the G star will be abelian with respect to this bracket. But most importantly, the space of left invariant of one bracket will be a real algebraic variety, and it can be put in a one-to-one correspondence between the set of pairs consisting in a Lie bracket on the Lie algebra G and a left invariant tree form, which is closed with respect to the differential induced by the Lie bracket mu. And now the Lie group L will act on the space of Dorfman bracket by change of basis, and so we can actually compute the infinitesimal action of such action, which is the following, a classical one. And now, fixing a generalized metric, we can put even more information on that space. So an inner product, which is built naturally from the choice of a generalized metric, and an inner product on the Lie algebra of L, which is the following. Now we are in the right position to, we got a group acting on a real algebraic variety, and so we are in the position to define what is the moment map of the action of L on the Dorfman brackets, which will be defined implicitly by this equation. And then what we managed to prove is that actually this modified version of the generalized Ricci curvature can be written in terms of this moment map, the moment map of the action of L on Dorfman bracket, plus some algebraic datum, which are, as in the classical setting, the killing form of the group, and the mean vector curvature vector of the metric Lie algebra. But we can go even further and specialize in some cases this equality. We know that on nilpotent Lie groups, both the killing form and the mean curvature vector are vanishing, and so if we pick our Lie bracket to be nilpotent, what we obtain is that this modified version of the generalized Ricci curvature will be precisely the moment map of the action of L on Dorfman brackets. This is what guided us when we wanted to understand the asymptotics in the nilpotent case. We will see that at the end of the talk. But now our main objective was to, in some sense, study the behavior of the generalized Ricci flow in the homogeneous setting. So we build all this moving Dorfman bracket approach, and now we want some flow of Dorfman bracket, which will be the equivalent of to the generalized Ricci flow. And so we introduced the following, the so-called generalized bracket flow. The following evolution equation in the space of Dorfman bracket, which starts from the initial one and evolves accordingly to the infinitesimal action on the moving bracket via the modified generalized scalar curvature, Ricci curvature. And of course, we can use the one-to-one correspondence and write this flow as a coupled flow of a coupled flow, one for the Lie bracket on the Lie algebra, evolving accordingly to a bracket flow, where the direction is given by this Ricci B, while the tree form is evolving accordingly to this modified generalized modified equation. Now we have to compare this the generalized Ricci flow and this generalized bracket flow, and to do that we just need to build out of a solution of the generalized bracket flow a family of generalized metrics. And what we did is the following. So we got the initial generalized metric at the origin on G plus G star. And what we can do is left translating this metric, the identity, via the left translations given by the structure of the left translation induced by the moving brackets and lifted, of course, to the generalized tangent bundle. This will give us an endomorphism at the point x, which can be collected and give rise to a family of left invariant generalized metrics. Now we can actually compare this family with the generalized Ricci flow solution. So we start from the initial generalized metric, we run the generalized Ricci flow, and we construct the generalized matrix out of the generalized bracket flow solution, as above. You know, what we can show is that the maximal time of existence of such matrix will be the same, and moreover, we can actually find elements in L so that we can conjugate the G mu T to obtain the solution of the generalized Ricci flow. And so this is giving us that the solution of the generalized bracket flow will be isometric to the solution of the generalized Ricci flow. And so in particular, the geometry or the generalized geometry of these two flows will be equivalent. And so what we can actually study the behavior, equivalently the behavior of the generalized bracket flow to say something on the behavior of the generalized Ricci flow. And that's what we do, what we did to prove the following blow-up behavior. So we start from our initial datum, and we run the left generalized Ricci flow from our starting left invariant metric. But if we assume that the maximal time of existence is finite, then what has to blow up is the generalized scalar curvature as the time up to plus infinity, as the time approaches the maximal time of existence. Maybe I wanted to show you the proof, but I'm quite late, so I should skip that. But as you remember, the generalized scalar curvature is built out of the classical scalar curvature minus a positive term. And so in particular, we know that, for instance, on solvable Lie groups, any left invariant metric will have a scalar curvature which is non-positive, and zero if and only if the metric is actually flat. And just by observing that, we know that on solvable Lie groups, this quantity will be non-negative again, and so it cannot blow up to plus infinity. And so what we obtain as a corollary of the previous theorem is that on solvable Lie groups, the solution of the generalized Ricci flow that starts from any left invariant initial datum is actually immortal. And this should have said the previous theorem and this corollary and the proof of the previous theorem are just built on some previous result for the Ricci flow by Ramiro. But exploiting the connection between the pluriclosed flow and the generalized Ricci flow, we can actually say something on the behavior of the pluriclosed flow. So in this time, we have to start from a solvable Lie group endowed with a left invariant SKT structure. And then the solution of the pluriclosed flow will be, again, immortal. This, as I was mentioning before, is some sense gives evidence of the validity of the conjecture by Stritz and Tian on the maximal time of existence of the pluriclosed flow. Indeed, for any complex Lie group endowed with the left invariant metric, we know that the first chain class is vanishing, and in particular, the first Hermitian class is vanishing. And so the conjecture maximal time of existence in that conjecture was infinite, and so this is actually an evidence. But this result is generalizing many results known in the literature, such that those by Bowling, by Ferrarietti and Vezzoni, by Roy and Lafuente, and then by myself and Luigi. So once we have the long time existence, the natural question is to analyze the asymptotics of the generalized Ricci flow. And to do that, we focus on the nilpotent case, since we have the moment map formulation. But of course, to study the behavior in that case, we need to normalize the flow. And this we introduce this normalized generalized bracket flow, just the previous bracket flow, but normalized in such a way that if we start from a bracket which has norm 1, the solution will have constantly norm 1. And then we defined what we call generalized algebraic solison, which are nothing but the fixed point of normalized generalized bracket flow. But these brackets can be seen in some sense as generalized solison in the classical sense. Indeed, if we have a generalized algebraic solison, then the metric built by the fixed one and then left translating on all the group is actually a generalized Ricci solison, which in terms of classical datum means that if we can find a real number lambda and a vector field such that the metric and the tree form satisfy the following equations. And then finally, what we showed is that if we specialize on nilpotent Lie group and we fix our left invariant metric and our closed form, which is now assumed to be harmonic with respect to the fixed left invariant metric, then what we managed to prove is that there will exist at least a generalized algebraic solison in the homology class of H0, up to the action of automorphism, of course. And moreover, we can actually give a precise description of the asymptotics in this case. And so if we run the generalized Ricci flow, the solution up to scaling will converge to an expanding algebraic solison in some adapted Cheeger-Gromov sense. Adapted in the sense of exact current algebroid, and so we have to give a precise definition of the Cheeger-Gromov convergence in that sense, and up to this, the solution will converge to an expanding generalized algebraic solid. So I'll stop here. Thanks for the attention.
Thanks, Elia. Are there any questions or comments for the speaker? Do you see any chance of addressing the conjecture for Lie groups, the one about the existence, but beyond solvable?
We are actually trying in these days to attack that conjecture. Yeah. But in principle, it's just a matter of bounding the generalized scalar curvature, but of course it's not possible in the general case, so we had to exploit a bit better the pluriclosed condition, I guess. That should be what.
Any other questions? Comments? Well, if not, let's thank Elia again.
Thanks.